Welcome to the TOEFL Listening section. In this section, you will listen to an academic lecture and then answer questions about what you heard. You may take notes while you listen. You will have time to review your notes before answering the questions. Listen to part of a lecture in a university class. You will hear the lecture only once, so listen carefully. After the lecture, you will answer some questions about what you heard. Some questions ask about the main ideas and supporting details. Other questions ask you to make inferences or connections between ideas. Answer each question based on what is stated or implied in the lecture.
Today, we will examine the fundamental properties of sound waves. I will focus on three interrelated concepts. These are frequency, which controls pitch, amplitude, which controls loudness, and resonance, which explains why some frequencies produce large responses in systems. First, I want to define sound in simple physical terms. Sound is a longitudinal pressure wave that travels through a material medium, such as air. At a fixed point, the wave appears as a periodic variation in pressure. We describe those variations by their frequency and amplitude, and by the wavelength that connects them. Frequency is the number of complete oscillations per second. The unit is Hertz. Human hearing covers roughly 20 to 20,000 Hertz. In music, the note A above middle C is often set to 440 Hertz. When frequency increases, we perceive a higher pitch. Wavelength is related to frequency by the speed of sound. In words, the wavelength equals the speed of sound divided by the frequency. For air at room temperature, the speed of sound is about 340 meters per second. So a 1000 Hertz tone has a wavelength of about 34 centimeters in air. Amplitude measures the magnitude of pressure variation. It governs how loud a sound seems. Amplitude can be described in pressure units or using a logarithmic scale such as decibels. A change in amplitude changes the energy carried by the wave. Doubling the pressure amplitude increases energy, but perceived loudness grows more slowly because hearing is roughly logarithmic. Now, resonance. Resonance occurs when a system is driven at one of its natural frequencies. Under those conditions, the driving input adds energy in phase with the motion. That constructive interference causes the amplitude of the response to grow. A familiar example is a tuning fork. Tap a tuning fork and it vibrates at its natural frequency. There are many everyday resonance examples. Blow across an empty bottle, and the air column inside resonates, producing a clear pitch. Strike a glass gently near its rim, and a sustained tone can ring. I mentioned resonance in a wine glass because it shows how a small periodic input at the natural frequency can generate a very large amplitude response. Resonance is not always desirable. In rooms, certain frequencies can build up between parallel walls. Those standing waves create nodes and antinodes and uneven bass response. Acoustic treatment changes damping and boundary conditions to reduce those resonant peaks. When we analyze strings and pipes, we use simple formulas for standing wave frequencies. For a string fixed at both ends, the fundamental frequency is the wave speed divided by twice the string length. For an open tube, the fundamental frequency is the speed of sound divided by twice the tube length. For a tube closed at one end, the fundamental frequency is the speed of sound divided by 4 times the tube length. Damping controls how sharply a system resonates. The quality factor, or Q, quantifies that sharpness. A high Q means a narrow resonance peak and long ring time. A low Q means a broad peak and quick decay. Electronic filters and instrument makers use Q when designing systems to emphasize or suppress particular frequencies. Engineers and acousticians exploit frequency, amplitude, and resonance in many applications. In loudspeaker design, frequency response guides the driver choice. In medical ultrasound, frequency selection affects resolution and penetration. In musical instrument design, makers shape dimensions and materials to tune resonance and balance harmonic content. To summarize, frequency determines pitch and wavelength, amplitude determines loudness and energy, and resonance explains why certain frequencies produce disproportionately large responses, because energy is added coherently at natural modes. Understanding these properties helps us predict and control sound in scientific and practical contexts.
Listen again to part of the lecture, then answer the question.
I mentioned resonance in a wine glass because it shows how a small periodic input at the natural frequency can generate a very large amplitude response.
This concludes the listening section. For more TOEFL practice tests and study materials, visit spinta.org.